a binary search tree. Now, it is a specific form that is ordered in nature, and the ordering means that between the children, in this case the left and right, there is a certain expectation in terms of what we want from this ordering, right? And that's the reason why we can use it for searches. Okay, let's take a look at the definition. Now, in the case of the binary search tree, or for short, we call it BST. So we have a root, and the root may have up to 2 children, the left and the right. And we want the maximum number on the left. So the maximum on the left is still smaller than the root. And we want the minimum number on the right to still be larger than the root. And this is going to be recursively applied at every single subtree of this tree. Which means that when we look at one particular subtree, which is this, for instance, rooted at here, then we look at everything on the left must be smaller than the root. Everything on the right must be larger than the root. Now, if it fulfills this condition, then it is considered to be a binary search tree. Now, why is it useful to have this notion of binary search tree? Now, when we have a particular structure like this, then we can conduct searches in a pretty efficient way. Now, let us think about this, right? So let's say we are given a tree like this, and we want to search for a particular number, let's say 65. Now, in the case of number 65, if we don't know anything about the way that a tree is organized, then essentially it's like searching in a collection arbitrarily, right? So which means that the most probable step here is to do one of traversals, pre-order, in-order, post-order, and we're going to check against that element one by one to see whether or not we can find this number. Now, which means that at every point of time, traversal is going to have a complexity of about ON, right? Linear, because you're going to visit every single node. All right, in that case, that is going to be ON complexity. Now, but if we are running on a binary search tree, we can make use of the property that at any particular node, we know for a fact that all the numbers to the left, well, it doesn't have to be numbers, but all the elements to the left are going to be smaller, and all the elements to the right are going to be larger, which means that we can decide whether to go to the left or to the right. We don't have to cover both branches of the tree. For example, if you're going to be searching for 65 and we're going to start at the root, now at the root, we can check whether or not 65 is equals to 44, but it is not, right? Then we can decide, do I want to go to the left or do I want to go to the right? But anything to the left of 44 is smaller. And since 65 is already larger than 44, then there is no necessity for us to go to the left. We can just go to the right. And to go to the right, then we will go on to 88, right? In the case of 88, which is the right child of 44, well, in this case, 65 now is smaller. So then we go to the left. And finally, we found this, right? Because 65 is actually here. Now, in the case of searching for 76, well, in pretty much the same tree here, except that now it's going to undergo a little bit of a different path. So we go from 76 at the root, not equal to 44, but larger. 88, smaller. 65, larger. 82, smaller. And then finally, we find 76. Okay. So the pseudocode of that can essentially be expressed in the following, right? We are looking for the key K, and the P is the element that we are currently searching, right? And in the case of this, what we are basically saying is that if we are going to an external node, which in this case, let's say to one of these things, for example, right? Then it means that we have not found the element, and which means that we cannot find it at all. So for example, if you are looking for 81, right? Okay, let's see how 81 is going to go. 81. So 81 is going to start at the root. Okay, 88 smaller, 65 larger, 82 smaller, 76 larger, 80. It's supposed to be larger, so I would go to the right. But in the right hand side here, there is only an empty child, which in that case, then I know that the search has failed. Okay, alright. Now that is the case, the first case. That means that we have hit nothing, which means that now we have been unsuccessful. Now otherwise, that means that we are going to be looking at a specific node, right? And we want to check whether or not the element of that node is the same as the key that we're looking for. If yes, then it's successful search. Now otherwise, we are going to make a branch, either to the left or to the right. We go to the left if the k is smaller, right? Otherwise, it means that the key that we are looking for is larger than the middle one, so then I'm going to go to the right. Okay, so this is basically the pseudocode. Now if we look at the complexity of this, then we kind of know that every time we check a number, we are going to make one step. We always go down, right? One step down. One step down in the case of this, which means that our complexity is going to be more or less the height of the tree, because at every level we are going to check exactly one node. So we start at level 0, and then level 1, and level 2, level 3, level 4, level 5. Alright, so now the complexity of the search here is going to be more or less the height in that case, right? Because for every single node, you're going to visit one at every level. Now, if we were to look at it in that way, for instance, right? So we are looking for this, so we start at level 0, and then level 1, we check 1, level 2, we check 1, level 3, we check 1, 4, and so on. So then as high as the tree is, that is going to be the complexity of the search. So which means that it's going to be O1 per level. So then in the end, it's going to be the number of levels, right? Now, so then the question is then what is going to be the number of levels for a tree of size n, right? N nodes. Now, we can think of it in terms of the different cases, but let's say in the worst case, you will have that tree that looks like in the linear form, right? And the tree that is in the linear form then is gonna have a height of n minus 1, right? Because the first one is 0, and then 1, and then 2, and then 3, and so on. And in that case, then this is still going to translate to O(n). Now, you could have a different kind of tree that in the best case, right? Best case, you want it to be as short as possible. And to be short, you basically want it to be, you know, as full or proper as possible, because then each of them is going to have 2 children, right? So in that case, you're going to be maximizing the capacity of every node, and then the resulting is that the height is going to be as short as possible for a tree of size n. Now, if this is d, right, which is the height, right, that we saw before, then we say that, well, in that case, then the number of nodes is going to be 2 of the d plus 1. Okay, minus 1, right? Okay, so if that is the case, then we can kind of know what is going to be this d in terms of the n, right? So we bring the 1 over, so now it's going to be n plus 1 is equals to 2 of d plus 1. So if we take the log base 2 on both sides, then we can write it as d plus 1 is equals to log 2 of n plus 1, right? Which means that now we can take the plus 1 and just move it to the other side, which is now log 2n plus 1 minus 1. And this can be simplified into just O log 2n. Okay? Alright, now the next question then is that how do we insert? Right? So for example, if we want to insert the number 68, how do we find where to put 68? Well, and remember that we cannot put 68 just anywhere, because we want to preserve the binary search tree structure of this. So that means that we have to put the 68 in such a way that it doesn't violate the conditions that everything to the left of a node is going to be smaller, anything to the right of a node is going to be larger. Alright, so let's say in this case, suppose that we search for 68 in the tree, and this is basically the before, and this is after, right? Now if we search 68 on this tree, so we start at the top. 68 is not 44, it's larger, but it's smaller than 88, so it's going to be going to the left. It's larger than 65, to the right, smaller than 82, smaller than 76. Hey, so we hit an empty spot. Now if we were searching for 68, we would expect to find it there, and since it's now empty, then we can put 68 there, because anyway, that's where we expect to find 68 when we are searching for it. Okay, so the pseudocode is given in this slide, and we are going to be searching for it first, and that is going to return us a node, right? And this could either be an empty node, that means that that's exactly where we're going to put it, and that's going to be given by this, which means that now we are going to insert a search key K, and this key, which is part of the tree, right, is going to be associated with a particular value. The value here is like another collection. For example, it's like indexing, so you might have the number, which is like an ID, and the V is going to be like an object that contains a lot of other information. So in that case, then we just expand the tree. Now in the case where we find an existing key, so because we find an existing key, means that it might contain some other object there, so we're going to replace that object with the new one that we specify here. Now then if we can insert, we can search. Now we can also delete, right? And we remember that even as we delete, we want to preserve the property that is going to still be a binary search tree. And in this preservation of the property, we want to take into account several possible cases. Now one case is when we want to remove a node that is basically a leaf node that has no children, right? Let's find one such thing, right? Let's say we want to delete 8, right? And 8 here doesn't have any child, right? So which means that to delete 8 is relatively simple. So we just need to go to the paragon of 8, and paragon of 8 now still has a pointer to 8, right? And we're gonna say, can you just cancel this pointer? And in that case, then we would have removed it, and that's relatively simple, right? But of course, you know, in order to remove something, just like before you insert it, you first search for it. So you search for 8, you find 8, and then you tell the paragon of 8 that to cancel the link to 8. And in that case, then we don't have 8 anymore within the tree. Now the second possible case is that the node actually has one child, and if the node has one child, that is also relatively simple, because in the case of one child, then we can bypass the node, just like we have seen how to remove a node in the tree with one child. We can bypass it. Now let's say we want to delete 32. So the first thing we do is to search for 32, right? So we start from the top, 32, smaller, larger. So here we find 32. And 32 here has a single child, which is 28. So now what if we just want to remove 32 out? So in that case, we can just directly link 17 to 28, and then we're going to cancel this link to 32, right? Now if we do it in that way, then we pretty much get the tree on the right, where we have bypassed that. Now the more tricky situation is when the removed node has two children. Okay, suppose that we want to delete 88, and we are going to start by searching for it, right? So 44, larger, so 88 is here. But 88 has two children, and if 88 were to be removed, then we don't quite know how to replace it. Suppose that we pick 65 to replace 88. That's not quite valid, right? Because 65 cannot replace 88, because then they are all these things. 65 already has two children. So then what do I do with all these things on the right hand side here, right? Because 65 already has two children. I can't quite replace it with 97 either, because 97 already has a left child, which is 93. So I can't put 65, let's say, as the right child of 97. So it turns out that perhaps that the best replacement is not even either of them. What we want to do is that we really want to find the best replacement. And the best replacement should be a node that is as close as possible to 88. And one candidate of that is basically the largest number on the left hand side of the 88. Now if we think of it as the largest number on the left hand side of 88, so which means that we have to go to the left and then we got to go to the rightmost thing, right? Now in that case, we are going to use that as a replacement. Now suppose that we find that the largest number on the left is 82, so then we can replace 88 with 82. Now, but in order to replace 88 with 82, we first have to remove 82. Now, but by definition, 82 can only have at most one child. Why? Because if 82 has two children, if 82 has a right child in particular, then 82 will not be the largest number on the left. Then the child will be. So now we know for a fact that the replacement, which is the largest number on the left, cannot have a right child, which means that it at most has only have one child, which is a left child, right? And so first we remove that number and then we bypass it. So 65, which is the grandparent, can go directly to 76 now. And then we are going to transplant 82 where 88 was. And if we do that, then we will get the 3 on the right hand side here, which is after.